Welcome to Lesson 14C, Equations of Particle Motion. We're going to look at particle motion, and the goal is to predict where a particle will go in a flow. So first, let's list some assumptions and approximations. Number one, the particles act independently of each other. We're talking about the air pollution particles. Typically, they have to be more than about 10 diameters apart. So if we have particles that are scattered around like this, and they're very far apart, we can treat each one separately. If they're real close together, like these particles I'm sketching here, they would act like a cloud or an ensemble, and we would have to treat them much differently. The particles would have a lot of interaction with each other. We're not going to do that case. We're going to do this case here. Number two, the airflow affects the particle motion, but particle motion doesn't affect the air motion. So in fluid mechanics, we call this one-way coupling. The benefit is that we can calculate the airflow first, the velocity field, ignoring the particles, and then we just calculate the particle trajectories for a known airflow. Some people call this a frozen airflow. Even if it's unsteady, we calculate the airflow first, and then we inject the particles and see what they do. The particles have no effect on the airflow. We call this uncoupled. The airflow is uncoupled from the particle trajectories. By the way, this could not be true unless one is also true. So the particles have to be far enough apart so that they don't interact with each other. So two kind of follows from one. Number three, for air pollution studies, the fluid is always air. A lot of times at SATP, but not always. We're going to assume that the particles are spherical, number four here, and each particle has the same density. I mentioned before that if the particles are not spherical, we need to come up with some kind of equivalent spherical diameter. And there's various ways to do that. We'll talk about that later. Now a little bit about notation. The air velocity field is always denoted by capital U, in general, a function of x, y, z, and t. We get U any way we can. Measure it, solve for it analytically, approximate it, calculate it by potential flow, use CFD, whatever. We get capital U as a function of x, y, z, and t. The air properties have no subscripts. Dynamic viscosity is mu, density is rho. When there's no subscript, that's for the air. Properties that have a subscript P are for the particle. So these are all for the particle, rho p, dp, etc. Obviously, there's no mu p for a particle. Particle path is denoted by vector x of t following the particle. So at any time, x is made up of three components, x, y, and z at time t. And then the particle velocity is little v vector, and that's a function of time as we follow the particle. At t equals 0, it's the initial velocity of the particle. And then at any general time, it has three components, vx, vy, and vz. And one comment here, don't confuse this V with kinematic viscosity nu. It's unfortunate, but in Times Roman font, which is what I typically use, the italic V looks very much like the Greek letter nu. When I print it, I'll do just a V like that. So be careful of that. Now let's look at the equations for a particle. We start with Newton's second law. mp, mass of particle, times ap, the acceleration of the particle, equals sigma fp, which is the sum of all the forces acting on the particle. So that's just F equals ma. Typically in fluid mechanics, we do it backwards, ma equal F. I'll just label these things. Mass of particle, acceleration of particle, which is a vector, and then sum of all forces acting on the particle, which is also a vector. So this is a vector equation. Or if we split up the forces into gravity and drag forces, we get mp ap equal F gravity plus F drag. And this I'll call equation 1. Let's look at each of these two forces independently and separately. We'll deal with gravity first since it's easier. Here's our particle. Gravity is acting down. This is typically in the negative z direction, but it can be in any direction you choose. There will be a weight on this particle due to gravity. The weight on the particle is the mass of the particle times g vector. And since mass is density times volume, this is rho p, volume of the particle times g. But there's also a buoyancy force, Fb, which is acting up opposite the direction of gravity. And the buoyancy force is equal to the weight of the displaced fluid. So the particle displaces some of the air, and the weight of that displaced air is equal to the buoyancy force. So working on these equations some more, W is equal to rho p times the volume, Vp, which is pi dp cubed over 6 times g. So that's the weight. Similarly, the buoyancy force, Fb, we're making this force positive downward. We're making this force also positive downward, so it's the opposite direction. Negative rho, not of the particle, but of the air, so there's no subscript. and then the same volume, because we've displaced the same volume of air as the particle itself. So those are those two forces. And the net gravity force is the weight of the particle plus the buoyancy acting on the particle. And since those are opposite signs with the negative sign on the FB term, we can combine these into our final expression for the gravity force. The net gravity force is equal to the pi dp cubed over 6 is common, rho p minus rho times g. I'll call that equation 2. That's our gravity force. And notice that it's a vector force. So we have the net gravity force on the particle in the direction of gravity vector g. So we have one of these forces done with. Now let's look at the drag force. This is aerodynamic drag. First, let's define a relative velocity. We use little v for the velocity of the particle. So v relative, this is a vector, is equal to v, the actual velocity of the particle, minus u, which is the air velocity. That's the relative velocity. It's the velocity of the particle relative to the air from the point of view of an observer moving with the air. And that's the critical part. It's relative to someone moving with the air. Let me do some examples to show what I mean, and this will be in terms of increasing level of difficulty. The first example is what we call quiescent air. That's just a fancy name for still air, which means u is 0. So VR is v minus u, and u is 0, so VR is just equal to v itself. And that makes sense. The velocity of the particle relative to the air, that's our definition of relative velocity. From the point of view of an observer moving with the air, well, the air is still, so you're just standing there, and the particle's moving, so the particle has the same velocity as the relative velocity in our definition. So here's the particle, and if it's moving in some direction here, that's also equal to the relative velocity. And then what we're saying is that the drag force will just be opposite to that direction. So we see that F drag is in the direction opposite of VR. Next, let's look at moving air, but a still particle. At least it'll be still initially. Suppose we just kind of drop a particle into the air that's moving, or the particle just kind of appears suddenly and it's at 0 speed. So here v equals 0, but u is not 0. So VR is v minus u. The v is 0, so it's equal to minus u. There's our particle. We have some air velocity in some direction. We can draw the negative of that vectorially, just the opposite way, same magnitude, opposite direction. And then we're saying that F drag is in the direction opposite of VR. This is VR, since VR is negative u. So the drag is in the opposite direction of VR, which here is the same direction as u. That also makes sense physically. If the particle's just sitting there and we have air blowing on it, the drag will be in the direction of the air, the same direction as u. So the above statement still holds. F drag is in the direction opposite of VR. Now let's do the general case where VR and u can be in different directions. There's our particle with its velocity, and it's in an airflow with a streamline that I drew like that. As you know from fluids, the velocity of the air is in the direction of the streamline. It's tangent to that streamline. So that's our u. And our equation for VR is v minus capital U. So we have to add these things vectorially. So first thing I do is put the opposite of u will be negative u, and then I have to add these two vectorially. So there's my v, and then this completes the parallelogram. The net vector there, which I'll call VR, will be almost straight to the left in this diagram. So we're just adding vectorially v and minus u. And now using our statement for the third time, F drag is in the opposite direction of VR. And so once we find VR vectorially, we can find F drag, at least the direction of it. So our summary statement is that aerodynamic drag is always in the direction of minus VR. And that holds for any general arbitrary case where v and u could be in any arbitrary directions. And I want you to know how to do these vector summations. It's not that difficult. If I give you a u and I give you a v, you should be able to complete the parallelogram and figure out where VR is and then figure out what direction the drag is. Now, what's the equation for aerodynamic drag force? In fluids class, we had some velocity v impinging on some particle or some object in general. And we know that if this particle is stationary, the drag would be in this direction. So vector F drag from fluids class was 1/2 rho v squared CD A, where CD is the drag coefficient and A is the projected frontal area. For a sphere, of course, that's just a circle looking straight at the sphere. If it's a car, you look at the car coming straight at you and look at the area that represents the frontal area. Well, the only thing we're going to do different is instead of CD, we're going to use CD over C, where C is the Cunningham correction factor. So we rewrite this as F drag is 1/2 rho V squared CD over C times frontal area. From fluids class, we always had V relative to the particle because the particle, the object, this is in general in fluids, this is a car or a truck or something. This is some object, not just a sphere. V was always relative to that object. Here, however, we had defined VR as the velocity of the particle relative to the air. So it's the opposite of what we had done in fluids. Mathematically, then, VR vector is equal to negative capital V. In other words, they're just opposite signs, equal magnitudes. So F drag is 1/2 rho, and then capital V squared is the magnitude squared. And the above equation from fluid mechanics is in the direction of V. This is a vector, so the right side has to be a vector too, and it's in the direction of V. This velocity here is actually a vector. We want our answer to be in the opposite direction of V because of this equation. So a kind of a clever way to do that, little trick here, is to write negative VR. That'll give us the vector and that'll give us the magnitude also. But since capital V is squared and VR is minus V, now let's put in the magnitude of VR. And this grouping gives us a magnitude V squared, which is what we want up here in our equation. And it gives us the correct direction, which is in the direction of minus V. So again, that's just a clever way to use VR instead of V. And then we have our CD over C, and then our area, we're going to assume spherical particles. So again, that's pi dp squared over 4. And let's just clean this up a little bit. We can combine the 2 and the 4, put the negative sign outside. So we have minus 1/8 rho CD over C, pi dp squared, VR vector, and then magnitude of VR. And this is our aerodynamic drag force on our spherical particle, and I'll call that equation 3. Now let's combine equations 1, 2, and 3. Equation 1 was MPAP equal F gravity plus F drag. We use equation 2 for the gravity force. We use equation 3 for the drag force. And one other thing, AP is just dv, little v vector dt. That's the definition of acceleration of a particle. It's just the derivative of the velocity of the particle with respect to time. So when we put all this together, one becomes mp dv dt, that's a vector, equal, now the gravity force, pi dp cubed over 6 times rho p minus rho times g, and then the drag force from the equation at the top there, minus 1/8 rho cd over c, pi dp squared, vr vector vr magnitude. I'll call that equation 4. And that's our equation of particle motion in an airflow.
But, sir, what about added mass? Doesn't that generate a kind of a extra drag?
Yes, Boris, that's correct for an accelerating particle, but we're neglecting added mass here.
Okay, thank you, sir.
Now let's just do a little practice with this vector summation. We're given a small particle that's moving through the air at speed v as shown here. So this is little v as I've labeled. Here's a streamline of air. The velocity of the air is parallel to the streamline. So at the location of the particle, this is at some instant in time, the particle is moving that way, the air is moving that way. We want to do a vector analysis to determine the correct direction of the drag force on the particle. And then we'll also add gravity. So I'll do part A first. This is just a matter of adding vectorially. So I drew this all very accurately on the computer. I took my u, took the negative of it. So this is negative u vector. And then I did a complete the parallelogram of v minus u. So we're adding up v and negative u. I get vr. That's this purple arrow. And then remember the drag is opposite to the direction of vr. So that is the answer, our proper direction of drag. Part B, suppose the net gravity force acts downward and has the same magnitude as the aerodynamic drag force. This is just an illustration. They're usually going to be quite different from each other. We're assuming that gravity acts down in this picture and the net gravity force is down therefore and has the same length as the drag force. So that's the net gravity force. So all we have to do here is sum these two vectorially like that. And so our resultant force we'll call sigma FP. This is the net force on the particle. And you can see vectorially, it is about a 45-degree angle to the lower left. And that's not immediately obvious. Have a particle moving at some speed v up here. We have a velocity of the air moving this way, and you ask, what's the direction of the total force? It's not obvious that it's down this way. The gravity force is obviously straight down, but the drag force, you have to do this vector addition, and then you do another vector addition between drag and gravity to get the net force. And that's just a qualitative expression of this final equation.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.